You're curious, it looks like it takes about 10 seconds to turn on the live recording on average. Not too sure if that affects us, but that's kind of interesting while we're bored and waiting. Well, looks like we can begin. Excuse me. Welcome back, everyone. So for today's class, well, we're just continuing on from where we left off on the first part of example one. And we should be able to finish this set of notes here today, but if we don't, if we need to take some additional time, that'll always be perfectly fine. We're not ever trying to rush through the concepts. I feel like they're all important, or else we wouldn't have brought them to class in the first place. So what that means, though, is this chapter one is relative to this assignment one, and that means assignment one is only going to be considered officially assigned once the very last part of the very last problem in chapter one is complete. So that means if we need an additional set of time to get through this, the due date itself is going to be modified and pushed back by the amount of time necessary. If, for example, we ended up finishing it on, let's say, Tuesday, the 21st, then the assignment's officially due itself on the 28th. That gives you enough time to actually work on the assignment, get questions answered, put your questions back into your document and that kind of stuff. So it's meant to allow you to have kind of a flexible schedule. But probably the best way to go through this course is the moment you get a chance, start working through the assignment right away. Because all of these kind of topics, whether it's math, statistic, or otherwise, they'll have a shelf life after you've learned it through the reading or been in the class. The faster you can start acting on that knowledge, the better it starts to solidify. You'll find you actually spend less time studying if you can get the work in as soon as possible. Some people that could be days out depending on your schedule, but if you get in a routine of always hitting that homework at the same time about in your routine, you'll be all set for this course. And I'm going to try to keep the assignments like you see in assignment one, all about the same length like we mentioned last time. I think that's the main announcements I have for today, but any questions or comments, folks, to start us out? Okay, well, the major thing that we were discussing last class, the major reason we didn't want to go too far into chapter one notes right away is we'll be using a huge calculator, RStudio, so this thing right here. And just to ask to survey the class on this one, to install RStudio, we were going through this link here, installing the base package R, and then the IDE, Integrated Development Environment, RStudio on top of it. Anyone have any challenges getting that loaded up into your machine? Okay, one student did show me something that's a little bit tricky if you're using a Mac OS. So if you're installing RStudio and you don't have a Windows machine, then you'd be going down to here, download install R. When you go to install RStudio, you just be scrolling down to the right operating system. I thought the tricky part is the base package R on, say, a Mac OS. So if that's you, click on this as before. And next, I guess it's not too tricky. I remember something being weird there. You want this third row, R for Mac OS, up here for Linux. And then at this point, it's all going to depend on your machine. So take a look at the chip you have. So this is the ARM chip for Apple Silicon M1, M2 chips. It's a little touchy because of, well, that's not a standard chip at all, right? So you have to be careful with which package you actually do install on your Mac system. Any questions about that so far, or any other challenges that came up with installing R or RStudio? Okay, well, once you've got them both installed, let me minimize this. Like I mentioned, you'd want to probably hide this icon here, delete this icon, unless you like just the pared down, very Spartan looking system right here. It works just as fine, but you have to put in a lot more effort just to do a simple task like import a data set. So usually what I do when I install this is I just delete that shortcut, but file access is denied, so I'll just hide it. There we go. This is the icon that you do want to run through. So opening this up, pulls up this right here. And now finally you're working in RStudio. We'll have a chance to play around with this a little bit today, producing some graphics, nothing too major. In chapter 2, we'll work on it a little bit more, but pretty much each class period that we meet, we start to use this more and more and more, with a couple lectures being odd exceptions. So back to the lecture notes. We'll pull up the calculator once we need it. I don't think we need that here. Let's just delete that. And let's review what we were doing last time before we finish off this problem here. We are discussing the difference between parameters, these symbols above, mu and sigma, versus the difference of the statistics, these values down below, x bar and s. The short of it is that the parameters describe the population. So in this situation, where the population is all women with this peripheral arterial disease, if you want to calculate the mean brachial index ABI, you would have to access every single member of this population to calculate that mean. We've discussed that's pretty much impossible for a lot of situations, probably this one as well. This is a strange looking disease. I don't know how you would even identify the population exactly. So what they do instead is we don't calculate these, we estimate them. At that point, we are doing inferential statistics. We grab a sample and we're estimating something about the population, the parameters, just through the sample itself. That means we have these great approximations. Well, I did say great, but really, for being totally honest, let's mention this again. These estimates are useless to us until we can describe what the margin of error is in making those estimates. So while these are great, they're considered point estimates. Because we're estimating an unknown with one number, one single point. We need to do a little bit better. So we'll give confidence interval estimates for the parameter mu, not so much for sigma, but we have to deal with it still. And that means, well, we just have to know what these values are, how to identify them. And that's what we're doing here on the last couple parts. So we identified the population as being all women with peripheral arterial disease. The study took a sample of 187 women with this particular disease. That's what we just said briefly. This sample is those 187 women used in the study. That doesn't feel totally descriptive, but we know the sample came from the population. So this already tells us at the same time, these 187 women do in fact have that disease. So now we need to do the equally hard task of describe the unknown parameters. By parameters, we once again mean these things up here. We have descriptions. Mu is the mean of the population. Sigma is the standard deviation of the population. But we also want to describe them using the context. So we just need to mention mean of what exactly and for what population exactly. So take a look at this study again. The population is all women with that disease. And what did they measure? The researchers obtained the ABI. So that's their measurement, the ankle brachial index blood pressure comparison. And they found down below, let's see here, there's a mean ABI of 0.64, standard deviation of 0.15. And this enables us to say this, mu will be the mean. We have to say the mean of what specifically? This is quantitative data, so it's data that would have a unit. Really complicated unit. We'll just abbreviate this to ABI. It's a blood pressure unit, so it's more complicated than that for sure. We'll say the mean ABI, because those are the values that they were calculating. I guess we can't highlight everything in yellow. It starts to lose its meaning. So it's going to be the mean ABI for not the sample of 187 women. It will be for all women with this particular disease. So for all women with, we could say peripheral arterial disease once again, but you might feel like it starts to get redundant after a while. This is still in context of what you said in part A, so you can just simply say with this disease. So any kind of shortcut like that in your descriptions is always totally fine. But if you feel like it's unsure, no harm in saying again, with peripheral arterial disease. It's just a mouthful to say and write each time. So that's what mu is. Mu is an unknown in this problem. And it says unknown parameters, so we're referring to the other parameter sigma. Pretty much the same statement. We're just going to say sigma equals the standard deviation of the ankle brachial index, just ABI, for all women with this disease. That didn't quite make the cut. Let me see if I can fix that penmanship there. There we go. So we've got the parameters down. Now we just need to state the value of the statistics next. Any questions at the moment, folks? Okay, this experience of writing down the parameters and just giving a qualitative description of them is pretty common, but we're usually going to be doing that for mu, not as for sigma as often, but it's good to know how to do that if we ever have to. And it is tricky because, again, when you're describing the unknown parameters, we have to know that mu is corresponding to the mean, but we also have to be sure to indicate right here, say the quantity that we are taking the mean, or you could just say the average of. I'd say that part is really pretty easy to miss. It's easy to say mu is the mean for all women with this disease, but then we miss something. Is it the mean height? Is it the mean blood pressure? Or is it the mean ABI, more complicated blood pressure? So that's the purpose of that part right there. And the next, just as equally easy part to miss is this portion. Anytime we indicate an unknown parameter, this feels redundant. I wouldn't necessarily ask you to describe the population and a parameter in the same problem, except for this introductory example, because of the redundantness of this. But if you are describing a parameter, you do have to mention the population here. We must mention the population. And we have to tell from the context which population we're discussing. When we said this disease, we were moving backwards to that disease there, which nailed the right population we were concerned about. So we did it, folks. That's the mu value, the sigma value. This room gets echoey sometimes. If you're curious, especially in Zoom, that can mess up the audio. I think it's because the heat is on and we just have echo through the vents or something like that. But any questions at all, folks, at the moment? Okay, last part is just state the value of the statistics. Let's grab this for a moment. This one is not as bad because we were kind of looking at those when we were highlighting this part. It says the results. Results of what? The results of considering the sample of 187 women. So when it says mean ABI 0.64, that wasn't the parameter whatsoever because it was targeting the sample of 187. And that's what made this a statistic right here, purely because it's describing the sample. Excuse me. So we'll write down here. Our book uses X bar to describe the sample mean. You may have studied statistics where it was used as Y bar. I would consider that synonymous, so you don't have to change your notations. But just knowing the reading, it's often, almost always indicated this way. So X bar is going to be 0.64 ABI. Not too sure the best way to indicate that unit, but at least we know what kind of quantity 0.64 is by mentioning that unit somewhere. And the next value is going to be S. S denotes the standard deviation of the sample, analogous to sigma that describes the standard deviation of the population. And down here somewhere, it says standard deviation was 0.15 ABI. So that's our rundown of this problem. Really, the major goal of what we were trying to do here is just show all the moving parts. In inferential statistics, we're very interested in estimating parameters. In our course, particularly this parameter here, mu. Other more advanced courses might give estimates for sigma. And we do that through knowing what the statistics are. But again, the larger challenge in statistics is writing down this right here. This is the hardest part of the whole problem in a full statistical analysis, saying exactly what you're estimating, which interacts with the population at the same time, and the quantity that you're dealing with, you're taking the average of. Lots of little moving parts. So the whole purpose of this example is just to show what those things are as we go from chapter to chapter. What we're going to get into next is a little bit of descriptive statistics in this chapter, which means we're going to take a look at data types, produce a bit of graphics. In chapter 2, we'll show how to calculate these statistics rather very fast. RStudio just makes super short work out of it. But we're kind of going at this course a little bit slowly for the first couple of weeks, only because of the weird setup of Math 3350. It has a prerequisite of Calculus 1. It's slightly appropriate because we use probability, and probability is thought of as being really an application to calculus. But we have no prerequisite whatsoever of statistics in this class. So just out of fairness, really, and getting everyone on the same page, we'll be going a little bit slow, chapter 1, chapter 2. So I apologize to folks who have taken statistics. It might be tedious at first. Chapter 11 is when we start going in the normal pace of the course. But let's keep on going. Aside from taking apart a statistical problem like that, other things we want to do in this chapter is identify the different data types that we'll be dealing with. We'll call them either quantitative variables versus categorical variables. And what the difference between either one is, variable is, as our author says, anything that you're interested in amongst the individuals. Individuals in the last problem were the women with the peripheral arterial disease. One variable would have been ABI. I bet you that study recorded lots of variables, like age would have been another one. Maybe some other demographic information could have been important for their health history, and so on and so on. There would have been potentially loads of variables in that study. When we say a quantitative variable, sounds like it's pretty self-explanatory. And a quantitative variable is something where you can take an average of and it makes sense. So that could be height, age, times, distances. Another way to say this, though, is for a quantitative variable, there's often units. There will be units. If we can't determine what the units are whatsoever, you might be suspicious it's actually categorical, even if it looks like a number. So to contrast that, well, first, any questions, folks, with a quantitative variable? Okay, so to contrast that, we next have categorical variables. You could call them categorical or qualitative. Similarly, if you called a quantitative variable numeric, everyone would pretty much know what you meant. But categorical variables are things where, well, its purpose is to categorize. Common examples are things like blood types. We could take everyone in class today, call it a sample. We'd have to know what the population is, so that'd be a really weird sample. But then everyone could then be categorized according to the blood type, or maybe your major, your college, things along those lines. Another thing that's tricky is something like a zip code, say 83401, stuff like that. Those look like they're numeric, but they're actual categorical. They're just geographical zones. It never makes sense to average a set of zip codes. It's not going to be a zip code if you average them, more likely than not. And so we consider zip codes as categorical as well. So this example here is just a reminder, just because you're looking at numbers is no guarantee it's even quantitative in the first place. It could be categorical. Well, any questions, folks, with the two data types that we're going to take a look at? Okay, there's a lot more to say here. And if you've done the reading in chapter 1, you might have noticed quantitative variables come in different flavors. There is discrete quantitative variables. Think of counting. For example, if the data recording is just the number of years that you are old, and all we give you is an integer value for every single individual, that's discrete. But if we're recording ages of individuals and we say, just take time of birth, calculate, say, number of hours that you've been alive, that's a continuous variable. Reason it's not in the notes is only because we don't make a big distinction of that in actual practice in this class. We're going to be treating all of our quantitative variables in the same way. Categorical variables are also interesting. A lot of times they're unordered. We call those nominal categorical variables. But when they do have an order, like say Monday, Tuesday, Wednesday, Thursday, some natural ordering, then they're called ordinal. But same issue here, if you saw that in the reading, that is pretty interesting stuff, but we treat all of our categorical variables entirely the same in this textbook as well. So the author is just trying to give a little bit more background information on different types of variables. So down below, here's a study with several variables being included. We actually have a data set relative to this problem here, so we'll take another look at it later, in a bit later. This is all about the forced expiratory volume, FEV, measured in liters. We're told that it is a primary indicator of lung function. It's going to correspond to the volume of air that you can forcibly blow, usually into some kind of device, in the first second after taking a full breath, full inspiration. If you ever had something really bad, like say pneumonia, you went to the ER for, they probably did this test on you. So this file, the FEV data file, contains the FEV values of a large sample of children, along with some description of each individual. So this is real data. Some study was investigating some relationships here. We have 1, 2, 3, 4, 5 variables in total to work on. They tell us a little bit more information. In the sex column, we have that 0 is going to correspond to female, 1 corresponds to male. Kind of a weird choice, though, to use numbers in that way. Reason for that is in a lot of statistical software, if you're producing plots, these sometimes are just thought of as coding variables, and it's a great way to separate one plot for a gender, another plot for the different one. It also says in the smoke column, 0 is going to correspond to non-smoking, 1 corresponds to smoking. It's kind of nice seeing zeros here, so it tells us all of these children at those ages were non-smoking. I think what they meant by smoking versus non-smoking is in their home environment, exposure to secondhand smoke. But they could have included the case that a 6-year-old has a pack of cigarettes. We don't know for sure until we read that whole study. Let's actually take a look at that study. I have it right here on my thumb drive, but I'm duplicating my thumb drive as well onto the Moodle website. So to find all the data, all the documents you need, just go to the chapter here. And this is the file that we're taking a look at, fev.txt. So here it is. It's a really large data set, so it's kind of jarring as you scroll through here. We have loads and loads of zeros. And as we scroll through, let's see here. Remember, this is the smoking column. I think I've scrolled through a 1. They do eventually show up. So this one is a 14-year-old with a 1 recorded here. Keep on going, and we've got another 14-year-old, a 13-year-old, and so on. So this is a massive data set. It's obviously really important. I don't know the purpose of creating this data, but this study was probably funded potentially by the government as well to investigate something. But if you really want to understand this data set, you can't just look at it, right? I don't know what the story is by seeing this blizzard of numbers coming at me. So what we need to do is come back over here and just work in stages. We're going to describe the variables. And then once we get back to that data set, we'll produce some graphics by constructing a histogram for the FEV variable and doing a little bit of work on it. We're not doing too much with this data set, but it's a fun one to take a look at. Before we do all of that, all we want to do on this particular example too is, for each variable in this study, we want to determine, is it categorical or is it quantitative? Now, I want to change this data set a little bit, only because this can come up in the homework as well. So let me just see if I can remember how to do this. I want to insert column to the left. So this data set probably didn't actually come out like this. There was something probably on the far left. It would have been referred to as an identifier. The identifier column is really important for us to discuss because that one is not a variable whatsoever. The identifier could be something like the name of the child, for example. maybe a coding variable so that we're protecting identities, that kind of stuff. It could have literally just been a listing, subject 1 in the study, subject 2, 3, 4, 5, and so on. Let's go that way. If this was a data set of students at ISU, probably more likely than not, the identifier column would have just been student numbers. So 6, 7, student ID numbers rather, 9 and 10. Oh, we want to go dots like this just to say it's a big data set and we just terminate it here so we can see it on the Word document. So the thing to watch out for is if you have a column like this is not a variable. This is tricky enough getting started with this kind of concept that let's spill the beans just a little bit on a homework problem where this is actually relevant, because I feel like this is something that's kind of a blind side on us on day one. If we go to the actual homework set, that's assignment number 1. Let me open the PDF just because it's faster. We're doing a problem pretty similar to this one. Oh, sorry, I missed a chat there. No, we're not using R for this problem just yet, but we should be using R coming up on example 3 is when it's going to come up. But for this idea where an identifier is not a variable, in the actual homework assignment, it comes up here. Here we're identifying all variables, and it gave us a hint, or did it? No, it did not. Well, yeah, it did. Here it is. I guess I didn't need to say that. But watch out for these kinds of things. The lake name is not a variable whatsoever. It's just the individuals that we're using in the study. The actual variables are the measurements that we make on each one of these lakes, which are the 53 lakes in Florida. Representative lakes, they say. I forgot to actually put that hint in exercise. I had some semesters where that was a tough exercise because of that issue. So that means we can now just go through the problem, describe our variables as either being quantitative or categorical. Just double checking my color coding here. So we have quantitative, categorical, and looking through these variables, which ones would you say is belonging to the quantitative column? Oh, sorry, missed that chat again. Yep, good call. It's going to be the first 3 columns are now considered quantitative. Thanks, Hayes. These are quantitative because there's a unit. This is apparent, possibly years is what we would interpret this as. FEV is measured in meters. We were told. Height, probably centimeters, something like that. So either one of these things has units. Averages make sense on all these. So it'll be age, FEV, our measure of lung strength, looks like the major part of the study, and height. That leaves just these 2 left over for the categorical variables. It does say if the variable is categorical, also describe its categories. So we'll say here, for sex, we have categories 0 corresponding to female, 1 corresponding to male, and we also have smoke, where 0 corresponds to non-smoking, 1 corresponds to smoking. So that's the breakdown of the data of the problem. Data emerges once we identify the variables and make these measurements on each one of the individuals relative to all the variables. So this part of the table is the data. Well, any questions at all, folks, so far? Okay, like we mentioned earlier, our goal in chapter 1 is mainly descriptive statistics. If you had this huge data set, the first thing you probably may want to do is generate some plots. But the way we generate plots depends on the data type. So that's why we're making a big deal out of the dichotomy, quantitative versus categorical. So when it comes to quantitative, we'll often use for the graph that we're going for, a histogram. Well, actually, let's not put this here. I forget. I should have that described down there. When the data is quantitative, we'll go for the histogram. If it's categorical, we'll go for a bar plot. Not that these are the only plots for categorical or the only plots for quantitative, but they're very useful, especially here for the histogram, in deciding if one statistical procedure is better than the other. So that's the role this plot in here particularly takes. Before we get into that, we're going to segue from this problem into doing some graphics for the categorical variable. I think this one is a little bit harder, so it's a good one to get out of the way just to show how it goes. Well, let's go down to our next example 3 down below. When we talk about the distribution of variable, we're just saying what categories exist, how many times those categories come up. And if we're dealing with a categorical variable, we say what are the categories and the numbers of times or the percent of times those categories could have came up. So let's take a look at this problem to get started. I honestly think example 3 is a tough problem to take a look at, because when you're dealing with a problem like this one, and you want to describe the variable, it's hard to imagine what the data set originally even looked like. This is a big summary, and if you were doing the study, you probably didn't record your data like this. So let's read through the context to get started, and then describe what would the data set actually really look like if you did the study. This problem says, criminologists have long debated whether there's a relationship between weather conditions and the incidence of violent crime, which seems kind of reasonable in a way. I'd see if it's really, really hot, people are more upset for some reason. The author of the article, is there a season for homicide? This is an old study from 1988. I think this has been used in a lot of textbooks. It's just kind of an interesting one to give. It says it classified 1,361 homicides. Even though we don't need this for the moment, this is not a bad habit. That's a sample size. So we can say n is 1,361, where n refers to sample size. We don't need that so much on this problem, but again, this is a good habit for when we're plugging in n into various formulas and so on. So we have 1,361 homicides classified according to season, resulting in the accompanying data. I believe this is a specific geographical region, but until we actually read the article, we wouldn't know. You're not required to look these up unless you're really curious about them. So it says, for each variable in the study, indicate if it is categorical or quantitative. The variable is categorical, also describe its categories. This is kind of a trick question in a way. It was meant to mirror the last problem where it had the same kind of instructions. There's only one variable here. That's what's weird about this table. It looks like there'd be 2 because it says seasons and counts, and it feels right because up here, that was 5 variables with the identifier we explained, not being a variable. The reason there's exactly 1 variable here is because the data set was probably generated in this way. Excel used to open up a little, oh, there it is. Just opened up in a weird way. So the people who designed the study probably had something along these lines. They would classify the homicide. This is the identifier. Maybe if they're going through an FBI database website, it'd be a case number or something like that. We're not too sure how they got that data until we read the study. After that, they would probably generate a new column called season, just because we're interested in the season it occurred. And we go from homicide 1 all the way to this +1. We're going down to homicide number 1,361. So somewhere down there, let's just terminate it right here. We get the idea at this point. Next, they'd have to do some research, start actually looking at these files. Let's just assume this one happened in fall. Maybe this one's in summer. This one would be in spring. I'm just making these up for just examples along those lines. But this is how the data set would have actually been generated. And what it tells us is there's really only one variable here. It's categorical, season, and the categories of that variable are just the 4 seasons of the year. Well, does that make sense to folks on the worry about that counts there? Okay, Other things that you could remind yourself though is counts could be a variable because what would the average of this really tell us about the problem? Not too much. And what's the unit on these in the first place? Well, the unit is just how many times the category winter was hit. That's just talking about the categorical variable in and of itself. It's not a whole new variable. So at the end of the day, we'll say here, there is only one variable. It's this one up here, season. We have to describe it. So when we see that the outcomes are just categories, we'll say down below, this is categories. We have to describe its categories. Some people would just list them out. That's a perfectly fine way to describe them. Or you could just simply say, up to you, this is stylistic choice. This is categorical. Hang on, let me try to fix my thoughts here. Categorical with categories. Being the seasons of the year. If you decide to go that route, that would be just fine. Any kind of description that's accurate to what we're seeing here would qualify. Well, any questions at all, folks, on dealing with these data here? Only because the original data set would have actually looked like this, where we're generating the actual homicides themselves. Then we're generating the categories for the categorical variable here. But what's going on with this table is, this is just a distribution table telling us how many times each one of those categories actually came up. So a table like this one, let's actually add this to the notes. This is a distribution table. That only describes the season variable. In particular, it's describing how many times each one of those seasons came up. So it's not really a new measurement in the study. It's just another summary after we've generated the data in the study in the first place. Does that make sense to folks so far? Awesome. And thought of it another way, we could have done the same thing for this one. We could make a table that says smoke. It would have categories 0, non-smoking, 1, counts would go here. Now we'd actually have to find these numbers, but that would just be a way to form a distribution for one categorical variable. That's what was done here to get this table generated. Again, that's really, really confusing when it's out of nowhere describing variables. We have to worry how the data is presented. Imagine you created that data. A little bit of role playing helps. Imagine you're the head researcher. What does the data look like when you're recording them line by line? That gives you the better picture of what the variable truly is, just season. And this was just the identifier, which individual in the data set. Well, this is a nice table because it gives us some idea of what's going on. Way more, well, not way more, but significantly more, potentially, homicides in summer in this region. But what we really want to do is not let this be the whole set of graphics in a problem. It's not even really considered graphics, it's just a data table. We can do a little bit better by creating an appropriate display for these data. So here we'll go for a bar chart. So at this point, we'll be using RStudio. But any questions at the moment with part B? I feel like this is the roughest part of the problem. Okay, so let's give this a try. Oh, that's not RStudio at all. Let me go here. In RStudio, the very first thing we want to do is start typing up stuff right here in this field. This is considered the script, but this is a great place to start putting in information, because if we have to modify our syntax as we go, we don't have to retype it as we would down below here. Using this region down below here, I do sometimes use it, but that's when I'm thinking of RStudio as just purely a calculator. For example, taking square root 25, that'd be a decent calculator problem. or doing something with like the normal distribution. Calculating probabilities can be done pretty quick here as well. But back up here, we're going to put in a line that generates this information. First thing I'd probably want to put in is the counts. So let's start by saying here, anything that feels descriptive in the problem, I'll go with just ordinary counts. So that's going to describe this column here. Some people will go equals. Other people will suggest use left arrow. It's not as big of a deal in this class, but more often than not, when I read other people's R syntax, that seems to be favored for one reason or another. I'll have to research that to tell you exactly why. Read that as counts gets whatever we put to the right. We could try something like this, 328, 334, 372, 327, but this actually doesn't work. There's a different way we have to actually create this as a column vector, the data type we need here. But it's good to play around. This is a whole brand new system, so not a bad idea to just try something, see what happens, and learn the behavior based off that. So once you have something here you want to run, I often say hit Control A, that highlights everything, hit Control Enter, and then it runs everything. Or you could just use your mouse. Highlight like this, click Run, and it'll run your code. And as expected, RStudio, well, R really is pissed off. It doesn't know what to do with the unexpected comma. So here's our solution. This is kind of interesting in a way. We must combine these all into a vector. So the thought is C with the parenthesis combines them. You have to go very back over here to close that parenthesis. Make sure your values are comma separated. If you typed in your values like this, that's totally fine as well. It doesn't interpret the white space as anything. I typically put in a little extra white space just so I can double check I typed it in accurately the first time. So this is more for error checking on my own end personally. Well, once we have all that in line, do the same thing as before. Either highlight and click Run, or hit Control A, Control Enter. Usually you're just holding the control button the whole time, and then hit A and Enter. So it's not pissed off this time, it accepted the result. Looking here over the left, we're told we have a value. So this is our environment here, which will contain either the databases we import or the actual variables that we define. It says it's numeric and that it's a column vector of size one column, 4 entries, or 1 column, 4 rows, the values we just put in. So we're off to a good start on this. And if you're doing this in the homework problem and something just goes completely awry, just take a picture of this, use a screenshot feature on your laptop or something like that, email it to me and I'll help you diagnose what's going on. If I can't figure it out, I'll give you the result because again, we're just using this as a calculator. So we want a graphic. We said the data is categorical, so we want a bar plot. So we go like this, bar. For me, it's easy to forget what these functions are. If you type really slowly and start typing in the thing that seems the most obvious, bar chart or bar plot, you'll find the function you're most likely going for. Instead of bar chart, RStudio uses bar plot, but just type it out slowly and it'll reveal what you're really going for. So bar plot, you didn't actually have to type all that out. You can go up arrow, down arrow, and just grab the function you want. And sometimes that's a good idea because now I don't have to worry about mistyping something. So this is a function. Inside this function, the input is going to be the counts that we determine. Be sure to use just parentheses when you're putting in the input to this function. Close the parenthesis here, and you're all set. If we hit Control A, Control Enter, we should see graphics emerging right here. So let's give it a try. Let me know if your machine is doing something weird. Control A, Control Enter. Ignore the error, it's just floating there as we get more things generated. And I have a bar plot over here, but that looks really, really bad. Couple things going on. I'm in a really limited resolution environment, and so there's a couple things I can do to fix this. You have little controls here where you can move this up to reveal more graphics or format the graphics better. You can move it down. But usually what I do is I click on button called export. Let's say copy to clipboard. And from here, it's just a little bit easier to move this around and get the graphics looking a little bit better. But by the way, this is not a good bar plot. Let's add our grievances on this. What would you all say is just not good about this plot? Yeah, go ahead.
It doesn't label anything.
Exactly. If we're looking at this, we're not looking at anything at all, right? There's no meaning here whatsoever. And so this can't be our plot for our final result in our assignment. We need to say what these numbers are at the same time. So we need a y-axis label, we need an x-axis label. A main title is optional because we know we're generating a bar plot in the first place. So we're going to build towards that step by step. Let me hit cancel because we're not satisfied with that. And as you mentioned, the major thing missing is those categories. So let's go back over here, bring in the categorical variable by listing out those actual categories. We need a good name for this, but we could just call it season. Left arrow to say season gets. C to combine a vector of results. You have to open a parenthesis. RStudio automatically closes it just as a quality of life little thing it does. And then we type these in. I'm going to do this wrong at first, but let me know what the mistake is that you would feel is going to go on here. Most people using RStudio, me included, would type in the seasons this way: winter, spring, summer, fall. But this actually doesn't work at all. This is pretty problematic. We try to run this all, it says, object winter not found. RStudio thinks this is a whole variable stored somewhere. Well, that's the way it's been written, and it can't find that. There's just counts. Anyone see what the fix is if we wrote this out? No worries if you're not sure, because once again, not meant to be a programming class in the
We
first
need
place.
to match it to the numbers, like the numerical ones.
You're correct. You absolutely do have to match it to the numbers. But we did do the number matching when we listed winter, spring, summer, fall, corresponding to the 328, 334, and so on. So we would have only made a mistake if we went spring, winter, for example. The thing that we're really missing here is we just need to indicate that this data we're trying to import or store is not numeric whatsoever. It's just a string. We do that by putting in a quote like this, close the quote. Now it's going to treat this as a whole different data type. It knows it's just a category now. Move over to the next one, hit Shift and the key to the left of the enter button for the quotes. Do it over here again to end the quotes. And by the way, because of those quotes right here, you never want to write syntax in something like Microsoft Word, because it turns out those quotes are not the same. It will just totally mess up your code. That's kind of impressive in a way. So back over here, put a quotes on summer. If it converts to green, you're all set. Then same on fall. So this is how season needs to be built out. Let's give it a try by running it once again. Go the method of just selecting everything you see, click on run. Well, there it is. We have season stored as a second value. But when we went to plot bar plots, it hasn't been included. We have to take this extra information, just throw it in the function. This is the worst part about the bar plot function. I think it has the craziest implementation because it takes a while to figure this out. But you know what you can always do if you're not sure what's going on with a particular function is just type down below here, help bar plot. And it generates really the same web page if you Google this and went to the R website, every piece of information you need about the bar plot function. It's way too much, but the thing we want is right here. We need the names of the labels, and that function is names.arg. So finally, let's come back over here. Names.arg, set it equal to season, and then you're all set. Watch out for this. I practiced my code today since it's rude not to practice this stuff before trying to show it off. I typed it this way this morning when I was practicing if I still remember how to do this. That doesn't work at all. Try run this. It says season not found, and that's because the variables here are case sensitive. So if you had it lowercase here, it's got to be lowercase here. But when I make an error like that, this is really, really hard to find sometimes if this description wasn't helpful to us. So again, if something is going wrong with your syntax here, just show me what it looks like and I should be able to identify it. When I make this kind of mistake, sometimes someone else has to help me see where that mistake was because it feels like it's invisible sometimes. Now, with that one change, we can select everything. Let me make this environment just a little bit bigger. Hit the run key, and that's better. Winter, spring, summer, and fall. So we've got what we wanted. I'll click on the export key, copy to clipboard down here. And again, you can format this any way you like. If in this formatting, I lost something because my categories are pretty wide. So you can expand it going this way if something got dropped off. We can still do even more to this. I mentioned you need a description going this way. Well, we have something. You could put down a lower statement here that says seasons, but that's kind of redundant at that point. We're clearly looking at seasons, so you wouldn't have to if you don't want to. It's more important to put something here. We have to express what all axes mean, so we need a y-axis label. Any questions so far with where we're at, though, generating this plot? Okay, so let's add just a little bit more. Starting to run out of horizontal space going this way. So just so I can see everything that's going in the bar plot function, if that happens to you, just hit enter and indent. Again, this is all white space. RStudio runs right through it and just goes to the next line here. So next thing we're going to add is a Y label. And I don't know the exact statement for that. So just type it in slowly. Y well, it's just Y lab is what it's indicating. I think I did make that mistake this morning as well. I tried Y label, doesn't work. There's no function for that. But if you go Y lab and you're using RStudio, it's going to always try to direct you to the function it thinks you're going to want to use. So this will be equal to, I want to give it a name. Let's call it counts because that's exactly what it is coming from our table. But if I do this, it will absolutely not work. In fact, RStudio is trying to suggest I use the variable here, which is even worse. Anyone see what's missing in this syntax? Exactly. This is going to be a string, so we have to describe it that way with more quotes. So here it is. Y label is set equal to counts. Hit Control A, run the whole thing. But maybe before I do that, here's another weird feature about this syntax. When we're writing functions, we often use the left arrow. Within the function, we use equality to do comparisons or set things equal to. And Eli says, how did you put in the slab again? Oh, the Y lab. So for this part right here, I pretty much just went Y label and hit enter and just went from there. Is that what you're referring to, Eli? Awesome, yeah. So one way to do this is, if you already know what the input is, the function you're using, you can just type in ylab and call that good. Right arrow and type it in. But as I was typing this in slowly, you also have the ability to just hit enter right here as it comes up. That's really helpful if the name of the function is really long, which occasionally happens, and it drops it right into your syntax. Well, this is a pretty good plot at this point. Let me know if there's other things you'd probably want to change and add to it. We'll give it a try. So hit everything, click on run. We've got counts now printed over here. If you take a screenshot of this, I would be okay with that. But again, sometimes it's a good idea to format things just a little bit differently to make it look a little bit more readable. Now, question for the class. Would you do anything to change this? Is there anything on this plot that bugs you? Yeah, go ahead.
I don't know if it's what you're looking for, but you could, make it a little more, professional by adding, us making it into a solid box and maybe raising the variables on the y-axis just a little bit so that it's all within a nice box.
Yeah.
Understand what I'm saying?
Absolutely, I totally understand. Yeah, that's the problem with this plot, and to me, it is kind of jarring. I don't know if everyone would agree, but notice it goes up to 350. This category is 372. Really odd plot. I think if you put this plot out, it's almost misleading in a sense because it's making this category look smaller in counts than it really is. We're thinking of this as being the maximum. So I absolutely agree. To me, that's pretty jarring. I'm not super picky on these plots. So if you sent this out in your assignment, I don't think I would be too worried about it. But if you wanted to know how to fix it and make it a little bit better, here's the next step. We need to change the limits of the y-axis here. So we go comma for the next input. This is going to be y lim. There it is, y limits. It says, well, literally limits for the y-axis. So our student is pretty helpful for this kind of stuff. The thing that's tricky though is we want to go from 0 to maybe 375, maybe 375 could work, maybe 400, something like that. Your choice on this one. But that means we're giving this a whole vector once again. There's 2 digits. So go C to combine information, go from 0 to, I'll leave it up to the class. How high should we go up to? 400 sound good, everyone? Let's go for that. I like the nice round numbers. Going up by 50 just kind of makes sense. Let's go over 400. Now this range contains all of our data. That's what we really want for a nice plot, especially if we were worried about people accusing us of being misleading when we're not even trying that in the first place. Now at this stage, either select everything and click on run, or Control A, Control Enter, and that's a beautiful plot. Now you can tell that this category exceeds the others and it's just under 400, whereas before it almost looked like we were saying it was close to 350. Now we have to include this in our report. And by the way, the problems that we're doing right here are pretty much just how the homework problems look. The way I'm solving this is pretty much how you might solve it. You might type things out. You don't have to use a digital pen. So I think a lot of people end up typing, or you could just print these out and just write this in. Or another way, just take ordinary paper, label this as example 3, part B, write in your description, and that's just fine. If you go that more traditional route, you still have to have your graphics, but you could just send these as a digital file to my email along with your assignment, or maybe just print them out on the very end, include it at the end, and you'd be all set. So imagine this is a homework problem. You'll do one highly similar. When it says create an appropriate display, we've got to put a display right here, or just append it to the end of your assignment. So it's all about how do you get this out. Whatever machine you have, keep in mind you always have great snipping tools available to you. On a Windows machine, the easiest way to snip something is hit Windows, Shift, and S all together. Your screen will go in this color, different in other operating systems, but functionality is the same. This little cursor is going to be the region you're snipping out of. And you can go like this. This is just one way to do it if you're not a fan of snip tools. Come back down to your document, hit Control. I'm not too sure what I hit there. Control V, and there's our display. So there's one way to do it. On these kinds of things, if you're concerned about printing out loads and loads of paper, I have a pretty strong prescription. So as long as you can read it, I probably can read it as well. So don't worry too much about that. If you leave it like this, no harm either. So use your best judgment on that. Let's delete this for a moment just to give some more options. Another way to do this is you can come back over here, click on the export key as well. There's a lot of different things. You could go save as PDF. This is if you're doing your assignment on paper and you just want to include your graphics with your assignment as an additional file. That'd work out just fine with me. You'd probably want to label the file as exercise 3, something like that, just so that they're identified. I think this is a better tool. Copy to clipboard. Use this region to reformat, and Last year, this button didn't work. I think it's because the RStudio wasn't updated. So we're going to try it out again this year. Copy plot. Come over here, hit Control V or right click and paste should do the job. Hey, it works. And there it is. There's our plot. So I guess they updated this. For folks following along on your own machines, any issues getting that coming out? Okay. I don't like that way. I like to snip sketch a little bit more, snip and paste a little bit more because look at all that white space you've got. But let's let this one just stand for our response. This took a lot of syntax. Usually graphics in RStudio are a lot faster. For a histogram, for example, it's just one line. So for this one, when you go to do it on your homework assignment, you ought to use this right here as a guide and just modify as necessary. So for everything that we do in class, if it has to use anything with RStudio, no matter how big or small, I'll always include the syntax here, and I box it out so it's easy to identify when you scroll through the work we did. So this is the guide. Give it a try in your homework assignment. If it goes sideways, if something doesn't work, if you're getting a lot of errors, send me a direct email and I'll help you work it out. If you can't get it working in a time that you want to submit the assignment, or you're having bigger errors and we need to figure it out, I'll just email you that plot because again, this is not meant to stop us from enjoying statistics and actually completing them. And this is one of the harder ones, I think, as far as graphics go. But we did it, folks. Here is the appropriate display of our data table contained here. It's only one variable, the seasons, and this is now telling us how many times a homicide in winter came up, how many times a homicide in summer come up, and so on. Any questions whatsoever, folks? Yeah.
Can we use Excel as well for the purposes of making a display?
Yeah, absolutely. Excel would work out just fine as well. If we were doing this in Excel, just to demonstrate it, I would probably go like this. Copy this down. There's going to be a couple times where I use Excel a little bit when it makes the most sense. But for a quick description here, an alternative approach, let me paste it in. For folks better at Excel, let me know if I'm doing this in a weird way. Then I copy the whole thing, go to Insert, and let's see. This usually does me pretty good. Recommended charts. Here's the bar chart. You could also give a pie chart. Sometimes this is discouraged because we're not very good as humans identifying proportions as well as heights. But that would be an alternative approach that would work just as well, absolutely. One of the things I have found is troubling in Excel is a histogram is actually a lot harder for no apparent reason. I think it's getting better. There might be interesting extra packages inside here where histograms are a little bit more manageable. But in the past, that's been a big chore in Excel. Other questions so far? Okay, so we've got the display. Last thing we're going to do is just describe what we see in this display using the context. The context being that these are homicides that occurred amongst different seasons. Let me see if I can get this a little bit better on one page. Oh, we don't want to change that. Okay. So any volunteers for the class? If you saw this display here, what's a 1 or 2 sentence write-up that you would put down to describe it? This is tough, right? Because there's like a million things you could say here. So you're kind of doing a choose your own adventure at this point. Let me say what would stand out to me first. Then we'll add an additional sentence. I would say here, among the season categories, the number of homicides, that's the counts that we see here, are, geez, I'm not great at spelling homicides apparently. I mean, I guess that's a good thing. The number of homicides are roughly equal. Now let's add maybe one more description here. But if you said this on your problem, it's true, they're roughly equal. I didn't say give me 3 or 5 complete sentences. This qualifies. All I want you to do is really think about the context, say something through the context based off the graphics we produced. Any volunteers for one more statement to add on there?
Maybe we can mention that it's all above 300 counts.
Yeah, that would be a great thing to mention as well. They're all above 300. Each season has over 300 counts. That would be great to add to the report as well. Any volunteers for anything further, or do we feel pretty good about our description here so far? Yeah, go ahead. I like that. That's a great thing to say on this one. I want to take off points if you didn't say it, but the reason I feel like that's a really good response is, if you go back to the very top, there's a question implied here. Is there a season where homicide seems to happen more often than the others? So they're debating if there's a relationship between weather conditions, incidents of violent crime, and you know what? There's a little bit of a blip right there. That could be a real effect in the population. There could be something statistically significant actually going on, or this is just random sampling. When we grab things by random, all the observations of homicides, these things jitter up and down just by random sampling issues all of its own. Let's add this to the report. Summer, the season summer has slightly more homicides than the rest of the seasons. At this point, folks, we've answered the question, but only from a descriptive statistics point of view. Here's where descriptive statistics gets pretty tricky. We're wondering, is that real? Should we give a conclusion to say, yes, in summer, there's slightly more, a higher chance of a homicide occurring than spring, for example? Should we say that or shouldn't we say that? This is really extremely tough to deal with. But this is what statistics is all about. This is a massive, massive preview. So if this looks pretty weird, don't worry too much about this. This is a procedure called chi-squared that we're going to come back to towards the last part of the semester. But the way we decide, is that blip real? Is it statistically significant? Is through a chi-square test. Here's what it looks like. We go down here. I'm going to put it down on the console and just write chi. Forget exactly how it goes, but RStudio is designed to help us. This is the one we want. Just using up and down arrow, we can go to this one, chi-squared.test. We only need to give it counts. In different situations, we might have to give something different if the hypothesis we test has a different description. But the test we're wondering is, are all the counts considered equal, or is there a chance that one category is different, which would imply 2 categories then? Run this, and I have a problem. Oh, I missed S. So you've got to be very specific. We said plural counts. Let's run that again. And this is yet another preview of what we're getting into in this class. So we're not going to add this to the report. This is going beyond the homework problem and the example problem we just did. But it's telling us the chi-squared probabilities for those counts, the seasons you see to the right, tell us that's the test statistic. Degrees of freedom are 3. We'll come back to that, but it seems to do, it is in fact because there's 4 categories, subtract 1. This is the interesting value. Oh, hang on, let me try to run this one more to format it. The p-value. This is fantastically difficult to interpret, but let's do it right here as just a further preview of what we're getting into in the course. It looks like we're not going to finish this document today, so we'll come back to it on next week. We'll push the due date back a little bit. But it's worthy to give a quick look at what that p-value is trying to say. So this p-value, let me make a screenshot. We might as well add it to the document. I'll try to format this better after class. And I'll call this right here, preview, information. Just as a way to say you don't have to do this on your homework assignment. So here's the p-value, 0.2578. Let's say exactly what that means. If there is no effect in the population, what we mean by that is maybe for this population, the incidence of a homicide is equal amongst every single season, 25% chance. So no effect in the population, chance of a homicide is 25% for all seasons. Then, well, we got some weird data, right? This has a blip that goes counter to that assumption. Equal categories, no effect. There is let's take a look. There is a 25.78% chance of getting data as extreme as ours. As extreme as ours, it means as extreme as that blip right there, deviating from equality, as extreme as ours, or more extreme, when the last assumption, no effect, is actually true. When the last assumption is true. So what this is all saying now finally is that this plot right here, sorry, let me try to fix this window. Oh, that didn't work. This plot right here, as soon as I can resurrect it, oh, dang it. This plot right here, sorry, I try to avoid scrolling up and down constantly since I feel like that could give someone motion sickness. Okay, finally, we're saying that if there is really nothing going on, that homicides can happen in any season, equally likely, this could happen about 25% of the time when we pull a sample size of 1,370 and so on, and we get a blip like that, as big as this or even higher among any one of the categories. That's pretty often. This can happen about 1 in 4 times. So we would say, looks like we don't have any evidence that there is a particular season that favors homicide. Looks like there's nothing going on in the population. But this was, say, 0.003. Now there is only a 0.3% chance of getting data this extreme. We would say that whole assumption is wrong. There is a season for homicide. There's no way these categories are likely because there's a very small chance of getting this data. That's what we say in statistics, but it doesn't mean it's true because rare events can happen as well. So if we really want to know if this effect really happens, study has to be duplicated, meta-analysis has to happen, but this is where it all starts. Try to find an effect at least one study and then begin replicating. So again, this is all preview information. This is what statistical methods are all about. Deciding after we produce the descriptive statistics, is there something real going on, or is this just random noise and a different sample might have had winter come up a little bit too, and this go down, for example. But any last question or comments, folks, with that preview? Yeah.
The values for the seasons were incredibly varied. What would our p-value be telling us?
Oh, that's a great question. Let's actually put that in. Let's put here, let's suppose in summer, there's something like 10,000 homicides or something weird like that. Let me run this. Our graphs are going to look crazy, but we can still go, oh, chi-square dot test counts. And my p-value is essentially 0. This is exponential notation now. So move the decimal place 16 spots to the left. It's essentially saying, if you make an assumption that there is no particular season where homicides are more likely, there is almost a 0% chance of getting such extreme data. So we have found then there is a season where homicide really is more likely. It's statistically significant at that point. But if you bring it back to 334, run this again, it says there's almost 100% chance of getting data like this when you assume the categories are evenly distributed. So this data is in line with the assumption no effect at all happening in the population. In other words, I'd say this is all pretty tricky kind of stuff. So again, we're going to look and delve into these kinds of issues in a lot of detail. But other questions or comments at the moment? Yeah.
Just because I'm curious, what's the cutoff to say it's significant?
That's super context sensitive. So if you're working in maybe something like the medical sciences, engineering, stuff like that, you might have to have something like 0.01 be your significance level alpha, or even smaller, in the sense that now significance would be below whatever this value is. And that's what was being said way up here, just to connect some dots, when they said, we didn't answer the question in gray because we'll come back to it, but at significance level alpha at 0.01 means a p-value needs to be below that before we go and say there's something happening in this population for this category or population of women. So again, highly context sensitive. A lot of times people might put a 0.1, 0.05 as specific values. And if this is really high stakes, we're going to describe type 1, type 2 error. This could be even smaller before we go ahead and reject a null hypothesis. So depends on where we're working pretty much. Other questions at the moment? Okay, well, have a great weekend, folks. We didn't finish this document. We took a little extra time doing some of the graphics. So that means this homework assignment here, the due date gets pushed out so that it's always a 1-week turnaround on the assignment once all the problems here are finished, so that you have full support here to look up. But have a great weekend, folks. If you decide to look at some of these things early and questions come up, don't hesitate to email, even over the weekend. Thanks, Hayes. Have a good one. Yep, take care. Any questions?
Sir,
Yeah, take care.
and have a good weekend.
You as well. Oh. Contrast, that's weird. Oh, it could be because your, yeah, I would probably call that either an X for the simplest version or just count.
Just count.
Yeah, or counts. And then you need on there a left arrow or equality, up to you. Then now down here, you'd have to have counts in the same case. Or counts rather, yeah. That was RStudio trying to call back your previously defined variable.
Did I need to click on that when it came up?
No, you did not. You could just keep on typing and override its suggestion.
So, and then to enter it, this is where I do like the control.
Yeah, either hit Control Enter or click the run.
Oh, okay.
Huh.
I wish I could scroll all the way down. But
Oh, you do have a scroll bar on there on the right. Well, it disappeared after a minute.
only gets me down like so far. Kind of weird.
Maybe double click on this part up here. Yeah, I think that gets you there.
Okay.
So unexpected in counts. Huh, but you had it defined that way. Wait a minute. Spring, summer, fall. You have count. You saw August season. Y label is count. Huh. Unexpected comma. So commas look good.
I don't have any spaces in there.
Yeah.
I do have a couple random spaces.
You know what
there,
you
but
could
there's
try,
nothing
though?
For that.
Click that broomstick icon there. This is going to clear out your environment,
Oh.
and maybe this can resolve what could be going on.
So should I just try running that?
Yeah, let's give it another go. I am flabbergasted. Oh, wait, no, it did get that in. But why did it put it in all caps? Counts.
I might just try closing it and rerunning it.
Yeah, something seems a little bit odd about what it's doing here, because you ran it in lowercase, it should have duplicated it back down there. That's a little bizarre.
I'll do some troubleshooting. If I
Okay.
figure out what it is, I'll let you know.
Let me know how it goes, and if you're having trouble with that on assignment, again, I'll just send you that graph, so we'll move past that one.
Yeah, and like, you know, he said I could always use Excel for something.
Yeah,
like that.
absolutely.
You know.
Yeah, yep, you betcha. Any questions?
So, 7.1 assignment, I still don't have my book. They got me my Japanese books. I don't have
Gotcha.
my English, this book yet.